speak about a brief introduction on characteristic classes, and well, especially I will concentrate on explaining about Stiefel-Whitney classes and point-rigging classes, because those are going to be very relevant when I come to speak about Cobordism groups, the oriented and unoriented cases. And the second part of the talk is going to be devoted to the signature theorem, to Hitzebrook signature theorem. And for that part of the talk, we are also going to need point-rigging classes, so that's why it's quite important to explain about them. So, well, the characteristic classes are cohomology classes, and we are going to be considering four very important types of them. Stiefel-Whitney classes, which I have already mentioned, they are classes of a real vector bundle. Chern classes, which are complex vector bundle characteristic classes, and point-rigging classes, which are, there is also a real vector bundle, and also the Euler class. Although I will be only concentrating on Stiefel-Whitney classes and point-rigging classes, we must take into account that all these characteristic classes have strong relationships between them. So, for example, when I explain about characteristic classes, we will see that I have to define them in terms of Chern classes. And well, there are also very nice relationships between Stiefel-Whitney classes and the Euler class, and point-rigging classes and the Euler class, and so on. So, well, here we have that every cohomology class, as you have in that cohomology ring, determines a characteristic class of principal G bundles. And why is that? Well, first of all, we're going to have an example of this abstract thing that we have there, BG. Well, BG is constructed as the space of G orbits of a contractible EG space. If we want an example, for example, what should be the classifying space of the integers, we need we need a space on which the integers act freely, then we close it out, and we have that this is. Well, for example, we could have another example, classifying spaces for Z2. Very, very nice and important one is the one that you already have there. It's about the infinite Grassmann manifolds, because, well, we have been talking about infinite Grassmann manifolds and using this notation. Well, this notation, if you see the similarity, is just the classifying space of the principal L bundles, line bundles. So, well, it's interesting to think about the definition of Grassmann manifolds being, these inclusions that we talked about on Monday led us to define the infinite Grassmann manifold, but we didn't really talk about it as a classifying space. And that is very interesting to see Grassmann manifolds as a classifying space, and we'll now see why. Well, here we have a map of a bundle map from a bundle, from any bundle to gamma n, which we were using the notation as the universal bundle over the infinite Grassmann manifold. So, well, this map induces unique homotopy class of maps between these spaces. So, if I draw this down as a diagram, I should have my bundle C, then the universal bundle that lies over the infinite Grassmann manifold, and well, this is a vector bundle for some manifold M. So if we have any map here, then, well, this map, as I said in the slide, induces a unique homotopy class of maps between base spaces. So, well, this is sort of also that. And then we can see that we can recall the pullback constructions that we also talked about the other day, and we can see that we can write this vector bundle as a pullback from this one. So we can write this as but then this means that any characteristic class of this universal vector bundle can also be pulled back by this pullback construction. So I get to that nice relationship that you have in the square. This means that if you have a characteristic class here, you can pull it back. But if you have a characteristic class of this vector bundle, you can also go the other way around and find your universal characteristic class. So that's why, well, that relationship between the pullback construction and the characteristic classes of this infinite Gaussian manifold is very, very important. It is something that is in common to all characteristic classes, and well, we usually refer to it as the naturality condition. So, well, going for Stiefel-Whitney classes, Stiefel-Whitney classes satisfy certain axioms. First of all, the existence axiom that you have there as part A, well, that they always exist Stiefel-Whitney class. Stiefel-Whitney classes for each of the dimensions in the cohomology groups. For the serial cohomology group, you have the unit element, and if you go above the dimension of your base space, then the Whitney classes are just zero, so just don't count. As axiom B, we have the naturality axiom that I've been talking about just a moment ago, and as you see, well, we have here the pullback construction just in the same sense as we had it in the previous slide. Only just that here we are referring it to the Stiefel-Whitney classes. So this is a very, very, very important axiom. Now, the weighted product axiom means that if you have the direct sum of two different vector bundles built over the same base space, then as you see, the Stiefel-Whitney classes can be added up as well. So the first Whitney class of our sum of vector bundles equals the first Whitney class of a vector bundle plus the first Whitney class of the other vector bundle. And in general, you have this nice formula here, which relates the direct sum of these vector bundles to the Stiefel-Whitney classes of the vector bundles taken independently. And also very important, one of the important axioms of Stiefel-Whitney classes is that, well, the ith Whitney class is a generator of the cohomology group of the infinite projective space, taking over set 2. That's also important. Well, now we're going to see some important examples. For example, what happens if we have two isomorphic vector bundles? For example, these are two isomorphic vector bundles. Well, then something that's very interesting in relationship to the Stiefel-Whitney classes is that if they are isomorphic, then each of the Stiefel-Whitney classes are equal. Another interesting property is that if we have a trivial vector bundle serial for Stiefel-Whitney classes. If that's a trivial vector bundle, then any of its characteristic classes is going to be serial, and that's a very interesting condition, because if it's trivial, then the characteristic classes are going to be serial. The other way around, it doesn't hold. I mean, you can have vector bundles with every characteristic class serial and not being trivial. So that's something that doesn't go back. And another interesting example is that, or property, is that if the vector bundle is trivial, then you have the Stiefel-Whitney class of this sum of vector bundles. One of them is trivial, the other is not, and that is just the corresponding Stiefel-Whitney class of the vector bundle that isn't trivial. You maintain this one. As this one is trivial, you can just take it away. Well, before I go on talking about Stiefel-Whitney numbers, I would like to point out that, as I said before, any characteristic class can be pulled back from the universal vector bundle of the infinite Grassmann manifold. And being that in that way, we have that this cohomology ring that you now have on this frame is very, very important, because in some sense all the characteristic classes live inside this cohomology ring. In particular, if we are looking over this ring over Z2, this is just a polynomial ring over Z2, and the relationships between the Stiefel-Whitney classes, well, there are no relationships between them, independent. So it's very, very important. And in a very, very similar way, we can define the cohomology ring for the oriented Grassmann, infinite Grassmann manifold, VSLN. The only thing that I would like to point out about the notation is that, well, I have written here the universal bundle without a tilde, and here it has a tilde because we are considering the orientation down here. But again, there are no polynomial relations between the Stiefel-Whitney